computer. Okay, looks good. So let's continue for today. We finished our discussion about how to concentrate power generators for power system modeling. In this case, I would like to continue with some examples about power system, about power generation and power flows. For this, I'm going to use Nordic Baltic example. So this is Nord Pool. So this is Latvian transmission operator AST homepage, but this information is provided by the Nord Pool market. So Nordic countries marketplace. And what we can see here. Now, first of all, let's introduce countries. Okay, this is North Europe. Here we could see Sweden divided into, I think, 4 areas. Here you can see SE1, SE2, SE3, and 4. Norway, 5 regions. Finland as 1 region. Estonia, Latvia, and Lithuania. So every country as a node, and as a result with its electricity node price. So first of all, let's discuss the generation portfolio. What is going on? And maybe one more comment about this UCTE. Okay, UCTE. About the, it's from Wikipedia, but whatever. We need just a picture to discuss. About the Europe, what is going on in Europe? Here you can see different united power systems. What does it mean, united power system? United power system, it means that it's a union of power systems, that independent power systems are united together with specific rules. So as a result, you have your power system rules, how to keep this power system parameters, and you have over your state power system regulation. So rules, what as a system operator you should do, or your power system must do, yes, to be a part of united power system. That's why what we could see here, there is a Nordic power system, Central European power system, no, United Kingdom and Ireland. They are separate because physically these are islands. Some comments about Latvian, Lithuanian and Estonian power system, because sometimes, more often, I will use these countries for, like an example, because now we're in Latvia here. And to have more understanding, yes, I need to say some words about this history and so on. So the Latvian, Lithuanian, Estonian power system connection and synchronization to Central European power system was done in this year, 2025. So this is a very new synchronization. Before this synchronization, 3 Baltic countries was part of no, it was, how to say, from the Soviet Union time, so it was a part of the circuit that contains of Russia, Estonia, Lithuania, Latvia, and Belarus. So these 5 countries was connected in a circuit and was operating like one power system, because there is a big difference in definition about united power system like it is here and connected to the power system. I'll try to explain what is the difference. Previously, operation was very easy and reliable. Why? Due to the idea how it works. There is a very powerful hydropower generation in Russia, in this West Russia. And these hydropower generators control this, okay, it was in the past, so controlled this circuit because they run first and then every single synchronous generator in this circuit just was connected synchronous to this huge power plant in Volga River to Russia. So it means that this power plant rule and control the whole circuit. For other operators, the role was just to keep all the connections, all the interconnections to ensure power flows, and if they wish, additional balancing power to control this cross-border power flows. Why? No, because market. Here we see European market, market liberalization, market price. Russia, of course, is not part of this market. That's why there is a different pricing system. That's why to avoid power flows from to Russia, you have this balancing power to try to keep these power flows. I think should be mentioned some descriptions once more time. I tried this describe previously, but physically, you understand, there is a generator, there is a load. And as we know from the basics of electricity, yes, the current flows in the way with the, how to say, lowest resistance. Otherwise, we could say that the power is consumed by the nearest load. In this case, if we have load and there is the nearest generator is in another country, it means that this load will consume power from another country generator. In case if we want to control this flow, it means that we need to make over generation somewhere close to this load to push this power in this low direction. Otherwise, as I said, it will consume the power of the nearest generation. In this case, so previously, the role of the system operator was to keep these connections, operation modes, yes, and balancing for power flow. For now, as we are part of united power systems, of union of power systems, it means that there is no main generator. All power systems follow the rules to keep operation in synchronous mode. So there is a difference. In case when you have this main generator, then rules the frequency, yes, rules, it is more easier to operate. That's why to make this new connection, of course, synchronization, so on, there was a new challenge for existing power generator to start this frequency regulation function. So as there is no main generator that rules the frequency, it means that every power system must follow the rules and follow the frequency regulation. That was a new challenge about this generator certification, because you need to check, could this generator follow the rules and fill the task. In this case, for example, for Latvia, we have three enough powerful hydropower plants on Daugava River, about 400 megawatts for Riga hydropower plant, about 900 gigawatts for Plavinių hydropower plant, and small 200 plus Kegum hydropower plant. Due to construction issues, the most powerful hydropower plant, Plavinius, was not able to certificate for this frequency regulation, for this primary regulation. And the main rule field, Riga hydropower plant and Kegum hydropower plant. What is more important, that this hydropower plant and hydro potential is very good in Latvia, but not so good in border countries like Lithuania and Estonia. In this case, Latvia play a significant role in this power regulation. Okay, let's go back to the transmission operator system and discuss what is going on with Nordic countries. Maybe once more comment about, we see there is Nordic countries power system. This is Nordic. Here we see from three countries, Norway, Sweden and Finland, but Latvia, Lithuania and Estonia connected to the Central European. What was the reason? No, this is a political decision, first of all. You see, you need to understand one important thing, because okay, we're talking about this European power network, about this specific and so on, but how to say, the tendency is very similar for, how to say, almost whole the world. When we start to talk about the power system, this is a very important thing, and very often political decision rules this power system development and operation, but not technical. Okay, for example, for Europe, for now, traders and the market rule the power system. In other countries, there is no market, so there is no this special layer for power system control, ruling power system. So the only system operator rules from technical point of view, rules the system operation. But the upper level always will be the political decisions, because electricity is so important that politics plays its role. Okay, let's continue with this picture. So, okay, maybe once more here. So, different power systems, Nordic and Central Europe. It means that they are not operating synchronous. It means that you can't make an AC connection between power system. It is impossible, because if you take a wire and just will connect two systems, you will have it, a huge current. Okay, maybe I'll paint just to draw a very, very simple. They should be the same length. Okay, you have two electromotive force, or EMF 1 and EMF 2 of power system. Okay, the same omega. So no omega, it is 2 multiple by p by frequency. So the frequency is the same, so rotating. Okay, these are vectors, they are rotating with the same frequency. The amplitude, so the model, the value, also are the same. But what is the difference? You understand, these are vectors and these are rotating clockwise, yes, rotating with the same frequency, so the same speed of rotating, yes, with the same length and so on. But the only reason they are not synchronous, there is an angle between these two vectors. And if we connect these two systems together by a wire, there will be the resulting vector. And this resulting, and due to this, this resulting vector will rise a huge current. And this huge current will damage a lot of things in power system. So this can't be realized. That's why the only way that is used, as I described it, for example, inside the power system, for example, in Japan, because there are islands with different frequencies and so on, very easy way is to use DC connection. That's why you convert AC to DC, and then you convert DC back to the AC with the right frequency, right angle, and so on and so on. So how to connect two systems and to keep them operate not synchronous. And in this case, due to there is a Baltic Sea, the connections are made by the underwater cables, DC cables. And here we could see this is Estlink, that DC to DC cables connect Finland and Estonia, one more connection Sweden and Finland, and Sweden and Lithuania. So there are DC cables. Thanks to these cables, we could purchase electricity. For example, Lithuania could purchase from Sweden, and so on. Latvia could purchase from Sweden as well. This direction or this direction. But we should understand this one important thing. It is possible that Finland consume generation from Sweden, but it is impossible physically for Estonia to consume Sweden electricity. That's why generation from Finland is consumed by Estonia, but generation from Sweden is consumed by Finland, but on the paper, Estonia by electricity from Finland. So two independent flows, real power flow and money flow. Okay. But what is interesting, what we need to discover here, two things. First of all, power flows, and generation portfolio. No, as an additional option, we could see different price and pricing system, because this is if you play in a market liberalization. Maybe a little off top, but maybe it will be interesting for you. I think you have this information in another subject, but just a small remark about this liberalization. Basically, if we talk about this power system development theory, no, it's not only for power system, this is theory about for systems, yes. There are two ways of development. In a way of liberalization or not. So what does it mean, liberalization? We give more options to the lower layer. Or centralization. No options for the lower layer. What is the difference on Latvian power system example? So Latvian power system was designed in a not liberalization layer. So basically, let's come here and to see the generation portfolio. So here we could see the curves. This is total consumption in real life for today. Generation. No, maybe some result for now. Okay, total consumption for now is about how much? Consumption is about 633 and import is 380. So it means that a half of Latvian demand is covered by the import, not generated in Latvia. Historically, Latvian power system was developed like a deficit power system, so can't cover by itself the demand through the year. So in some time period, of course, it is possible over generation because Latvia has very, very good hydro capacity and could cover all the load by hydro power if you have enough water. This is the reason. If you have enough water, if you don't have enough water, you don't have a generation. Next step, Nordic country, district heating system, thermal power plant that produce electricity and heat. In this case, the idea was thermal power plants always operates on a nominal power to cover heat consumption and additionally produce electricity to cover base consumption. What is more? No, what is more in case of more consumption, more load? Other load is covered by a hydro if we have water, and not by the nuclear in Lithuania. So in Lithuania was built a nuclear power plant, yes, to cover this load for all Baltic countries. Historically, but when Lithuania joined the European Union, one of the rules of joining was to close nuclear power plant, and there is a great decrease in power generation in this region. What is more, next step, this is liberalization, market condition, and so on. In market condition, as you could see here, we start to play together with other countries with very powerful generation, for example, Sweden. If we come here to Sweden, we could see, of course, it's not it is a real situation for now, but if we talk about the potential, the total production for Sweden is about 24 gigawatts power, yes? Power, no, gigawatt power. So for now, the production is only 15 gigawatts. Besides, Sweden have a lot of nuclear, a lot of hydro, a lot of wind, and as a result, a lot of over-generation. And Sweden is exporting electricity, you see this, and selling it. Due to very cheap power source as nuclear, because nuclear is the cheapest electricity. The second cheapest is hydro, because water costs nothing. The only what you need is to build this hydropower plant and maintenance. But electricity costs nothing. For power and for nuclear, okay, you need this fuel, but you produce so much power that is very, very, very cheap. In this case, Sweden is selling electricity, and this electricity is more cheap than you could produce locally. In this case, there is a very interesting situation that was not discovered previously when it was, how to say this, Soviet time, no, before this market and liberalization. It is very often it is easier to buy electricity. And maybe one more remark. So this price for electricity for everyone in Latvia is set by the North Pole spot. It's a spot price, and this price, if we simplify this definition, is determined by the more expensive generator. What does it mean? Okay, you have a cheap electricity. You could provide 100, and you have expensive electricity with price twice bigger, but the load is 120. So cheap could cover 100, expensive could cover 100 more. But without this expensive, you could cover the whole load. In this case, what do the market? Market say, okay, that's the reason you will get all 120 megawatt what you need by the price of the most expensive generator. That's why if you have in your portfolio generation type more expensive, for example, thermal that use fossil fuel, is quite expensive. Sometimes if you talk about this wind could be very expensive as well due to this investment and maintenance and so on and so on. That's why the price would be high enough. And it is cheaper not to run expensive generator, but to purchase electricity. And you are suddenly in a situation that you not have your local generation, you are importing electricity. And interconnections, lines that transmit this electricity to you are become so important that in case of any trouble, of any interconnection, disconnection, you will be in a huge trouble. Why? Because you don't have your local generation to cover the load. And the only way is a blackout or special automation, how to save your system. To disconnect the load and keep the balance. To decrease the consumption, okay, we lost 100 megawatts. Import, that means we need to decrease consumption by 100 megawatts to disconnect the load. That is the way. Okay, but this is in case of problems when we have run this auto-frequency automation. We will discuss about this automation a little bit later. But now to continue the main topic for today's lecture. So yes, this is very interesting situation for this if you don't have enough generation. What is more, this mentioned in our introduction that we have a new challenge about the huge number of renewables with unpredicted generation, because it is sunny, there is a cloud, there is a huge drop. If you have a lot of generation, there is a huge drop in generation if you suddenly have a cloud or something else. So not stable and very good forecasting generation for every time moment. And you need to balance to cover all the load every moment. You need to balance these unpredictable renewables. You need to balance system in case of any trouble, disconnection, fault, and so on. That's why to keep this system alive, you have one more market. I say, no, okay, we will talk about, we have more markets, of course, but just, you have balance in market. And in this balancing market, I should to highlight one more very important moment about plan and reality. Making the operation plan for the next day, you need to plan the generation for every time moment, to plan for electricity selling, purchasing, and so on. But the reality is that you can predict the load, no, consumption for every time moment for the next day. But this is just a prediction. The reality always will be a little bit different. That's why you need a tool, yes, in real life to keep it in balance. For example, it was predicted the load 100, but the real load was 120. You need 20 more megawatts of power. How to get this megawatt? Because all generation produce so much power as it was planned based on the market trading. That's why there is a special intraday market, additional market. Then they say power for, or for balancing, or for unplanned cases. For example, I was planned to produce 100, but I have some troubles. I can't produce 100. I can produce only 800 or 80, 180. I can do 20 less. What to do? I have an agreement that I will produce. That's why I go to the market and buy 20 from another generator how to say it, to make true all like it was planned. This is in case of something goes wrong, yes, but in case that the load is not like it was planned, we have additional powers for balancing, and one we do need this market, because what is the idea? Okay, I'm a generator. I would like to produce power and sell, but I'm not producing and I'm not selling. I'm just waiting for case that maybe system operator will need my extra power or not. So that is the fee for generator to be ready to, or not for production, but for to be ready to produce in case if we will need this. That's why this is a fee for this special offer. And it calls balancing market. What is more for regulation? In case of trouble, as I mentioned, when all happen very fast, we need a fast response as well. That's why there is a special market for cases of trouble and fast response. That's why there is special market. And if you wish, I open this Fingrid homepage. This is a Finland transmission system operator and system operator as well. Very good in English homepage. You could go to open data, reserve market information, and you could see this fast frequency response, for example, FFR. What is it? Definition, powers, prices. What is it? FCN, FCD, FCRD. Yes, so we have a lot of very interesting information about how much, what is the price, and so on. So this is just a small overview for you to understand that for now, based on the market, power system operation is very, very complicated and as a result expensive. And maybe one conclusion based, for example, on latent power system. Sometimes, for example, like it is now, based on this market, we could have very, very cheap electricity purchased in Sweden and not generated locally because local generation is much more expensive. Or in case when we don't have where to buy, for example, Sweden don't produce, have troubles with interconnections, electricity could rise and this price could be several thousand for megawatt. This is price for megawatt, several thousands for megawatt. That's why we have this fluctuation with high amplitude for price. Okay, so short overview. What else? What else I forgot important to say? Yes. Okay. And yeah, I just mentioned that Lithuanian nuclear power plant was closed. So as a result, Baltic countries are deficit. Once more, Finland power system was deficit as well. And traditionally, before the war, that is now Russia and Ukraine, Finland has its own agreement with Russia to purchase cheap electricity from Russia. So this was an exception for Finland for this in this market, that they could have additional agreement out of market and purchase cheap electricity from Russia. That's why there was a huge flow to Finland. And to be true, Finland had an option to sell cheap electricity from Russia, like it is in Finland electricity on the market. So a good option for income. But for now, yes. Okay, Finland now finished to build a nuclear power plant. For now, that's why they can import only from Sweden and to keep alive, thanks to nuclear power. Because as you see, thermal not very efficient, is expensive, okay, for now it's windy day. They have enough of wind, but if the wind drop, you see how much deficit you will have. You need to cover this deficit, and this is quite complicated. That's why these renewables, very, 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 very complicated question about you need always to keep power to replace these renewables in case if we lost this power. As I mentioned several times, as example, let's see what is going on in Spain. Spain blackout. Okay, maybe in Spain there is a little bit different problem, not with active power, but with reactive power, and this drops in voltage because they were able to keep balancing with active power and with frequency. So these fluctuations with high amplitude with renewables was covered by the balancing of active power, and the frequency was good, the active power balance was good, but we haven't talked about this before, but okay, I mention that there is, there is not only an active power, there is also a reactive power as well. And reactive power flows in system R as well. And reactive power is very important for voltage. And as we know, we need to have a right voltage, so we need to keep the voltage level for power system because voltage is very important. And in case that power station for voltage regulation, for reactive power regulation, okay, maybe more clear is to say that power stations that makes the regulation of reactive powers for power system operation was disconnected due to a high production of renewables, because renewables don't produce reactive power, so they don't have this option. So what is the idea? That power plants that could control reactive power and to control the voltage was disconnected due to a high generation by renewables. Renewables can't do this task. As a result, voltage fluctuation, and due to this voltage fluctuation, started problems. So this is a case of problem, not an active power drop, fluctuations and drop, as a result frequency drop, but not option for reactive power regulation, as a result fluctuation of voltage, and then the same case to the blackout problems. Yes, so this is one more thing, voltage reactive power regulation. This is not so, how to say, highlighted, I'd say, because there is no special market. It is not, how to say, so controlled by the operator, because operators have possibility to rise and drop voltage using transformers in real time, and so on and so on and so on. But there is a rule, and special power generators should follow the rules, and if they follow, everything is okay. This is how it works. But in case that you don't have these generators who follow the rules, these rules, oops, you have troubles. Because our generation, for example, renewable generation is a different category of generation, different type, and they have different rules, and they don't follow this voltage and reactive power. So this is not their role in this play. Okay, that's it. Okay, so let's go next to the next topic for today, and let's start about talk what to do if we have troubles. How to save power system. So we have just discussed, we have plan, production, generation, balancing for different deviation of prediction and plan and so on and so on, so on. So everything goes okay. But for example, if we see this picture, this real situation, we have two DC cables, 800 and 700 megawatts. And oops, fault or problems with electronic because conversion AC DC to AC now it's made by electronic, high power electronics. And for example, this was the first cable built and a very long time of operation. The frequency of faults, of electronic faults, was about once per month. No? So powerful electronic is not so reliable. This is true. Okay, for now it's much more better, but in case you should be ready for such disconnections. And if we see for Latvia with consumption 750, yes, and we know with all these three countries can't produce so much power as they consume, hope you lose so huge power. What to do? Balancing? No, balancing is about 30 megawatts, for example, for our countries, because balancing is deviation. What is predicted and what is reality. So prediction is not so bad. So we could produce good enough and you don't need so much power for normal balancing. And in case of disconnection, as I mentioned, that you suddenly lose this huge power and you need fast response because you don't have time. The only time you have is the system inertia. So what system inertia provides you some seconds, milliseconds, yes, for you based on situation to restore the balance. But how to do this? That's why you have, how to say, the last soldier protection, system protection, and it calls out to frequency automation with a very, very simple idea. You can find more power to generate, so let's disconnect the load. So we decrease the load to restore the balance. That is the idea. Idea is very simple, but the question is how to implement this idea. And in different countries, there is a different implementation. Because you see, what is the main problem? You, as a system operator, see that frequency starts to drop. Okay, you understand that there is problem because you have normal frequency of 50 hertz, normal system operation deviation. That is okay. Oh, as I mentioned this. That's, for example, I think I can show you some digits. Okay, just need to find where it is. Some digits about maybe here. Okay. Some interesting digits about these rules. Okay. we will discuss later. Examples. Not here, maybe here. This is about frequency. Okay, not to waste time, I'll find a little bit later. I'll find this a little bit later. Yep, but little bit, okay. But just to say some digits for you, so some numbers to be correct. So normal about 50 plus minus 50 millihertz, it's how to say normal deviation, plus minus 150 millihertz, yes? That means that you need to make some action to not to restore frequency, but okay, to push it back to the value of 50. And if you have more, you have troubles. That's why you have a special set point that you understand that you have troubles because so big deviation from 50 hertz means that normal or how to say mode operation is not successful and you have troubles. That's why you have a special set point of frequency that you understand that you have a drop. No, we'll talk about the set points and so on a little bit later. Just a small introduction about this auto frequency automation. And you have a set point that you understand you have big troubles and it's time to disconnect the load. But come back to the balancing. It is a question how much load do you need to disconnect because you don't have a monitor with value. Oh, sorry guys, I have a deficit of 100 megawatts. System operator in real time don't know what is the deficit. There is one way how to plus minus evaluate the speed of frequency drop. So delta F differential. So the speed of decrease frequency based on this power system, total load, inertia, power generation, system capacity, network topology, and its resistance, impedance, and so on. So this speed could be, could represent the deficit. But this still is not very accurate. That's why still the main idea how to disconnect the load is to use different doses of portions. So we disconnect step by step some amount. Okay, we have this deficit. Okay, we disconnect. Oh, not enough, still is dropping. Disconnect more. Okay, once more, a little bit more, and so on. So it means that we have different stages. And okay, it's time to show you some pictures. This is a good picture for you to describe. So this is frequency, this is time. You have some trouble, something happened, disconnection, linear, line generation, and so on. You have this frequency drop. And this is, you see, the first frequency set point that automation understand that there is a problem, a trouble, I'd say. Normal operation is not possible to keep this problem, so this is the way, this is the time for under frequency automation. And in this, if the frequency drop to this point, this is the first stage of disconnection. If frequency continue to drop, goes to the node dot C, it means that this is the second set point of under frequency automation, and we disconnect more load, and so on and so on and so on, until the frequency stabilize. What does it mean? So if for a time moment there is a balance between generation and the demand load, frequency stays with the same value, so like it is in J. And it means that we don't need to activate another stage. And for example, what we see here more, 1, 4, 5 different scenarios with different deficit. Because if you have more deficit, you have, as I described, more high power or more high speed of frequency drop. You see this. And the idea is of this under frequency automation to restore the balance, so to disconnect so much load to keep the system in balance. That's why there are different stages. And there is the first very interesting question is what set point to choose and how much load power connect to every set point. And for this question, there is no an ordinary answer, because for every power system, this is decided individually, based on power system specific and, how to say, trouble experience. For Latvian power system, it was designed so reliable that we don't have any statistic for system level faults. That's why we don't have this under frequency automation statistic as well. That's why there was a decision. It is known what is a, because as I said, there is normal deviation, there is emergency deviation, this is critical deviation of frequency when we start under frequency automation. And there is known, this is low frequency, the frequency level that system is dead, blackout. This is about, okay, of course it depends again on power system, but it is about 47, 48 hertz. Yes, this is a critical value when, so it is over, the game is over. And in this, so between this, the frequency for stand in this critical frequency with the same step, there, I think, is, if I'm right, 18 stages. So we decided to have 18 stages and to connect some, okay, so I say some hundreds megawatts. We will discuss more about this, how much, a little bit later, but just for now. So if you have, okay, about, let's say about 40%, about 40% is connected, I'd say, okay, let's say in percent, this is more, this value will be more, how to say, more interesting. In about 40% is connected to this under frequency automation. Okay, and then, so yes, maybe once more to recap these set points, the idea, and let's talk about some issues and about some experience in another countries, and this will be all for today. So, some specific issues. First of all, I would like to show you this feature. You could see there's a frequency of 60 Hz because this picture is taken from the United States, but whatever. We're not interested exactly in values, but we are interested about this frequency drop speed. And here you could see the example about what is going on if we lose 10%, if we lose 30%, 50%, or 100%. What happened? And you could see the difference in speed, yes? And for example, you could see, okay, sometimes you have, okay, this is based on the power system energy as well, but about the time. So sometimes you could have 8 seconds, sometimes you have 12 seconds, sometimes more, maybe you could have a minute, yes? But you understand that we are talking about very small time. And in this case, it is very clear that only automation could deal with such tasks because people, operator, human, can't make decisions, send signals, and so on so fast. This is only task for automation. What is interesting and important? Okay, I need to open another picture from here. No, this. And I need to show you. Okay, the same was here for with 50 Hertz. Sorry, so okay. As I mentioned, for example, for this, yes, in case of 48 Hertz, when we have end of the game, you see, for this example, you don't have enough time. But I would like you to show this feature, and this feature is very, very interesting and very important for understanding how this blackout is going. How this, how to say, instead of all the protections and things could appear. How what we see here. Here we have some border lines for generators. So the idea is that low frequency, no, high and low frequency as well. Why I'm not talking about the high frequency? Because it is quite easy to deal with high frequency because you just need to decrease generated power to decrease the frequency, and much more complicated to deal with the low frequency because you need to produce more to produce more, you need a source. You need a generator, power, capacity, and so on and so on and so on. That's why frequency drop is more dangerous and interesting to discover that we have over frequency. So we have borderlines that says how much time generator could operate in a case of low frequency, no high frequency as well. So if we have problems, we have frequency drop, we need to restore balance. But for this time, we have one more challenge with existing generators, because this course says that for example, with frequency 49 hertz, generators could be in operation for 100 seconds. Because low frequency is dangerous for generator as well. And generator protection will disconnect this generator in 100 seconds if frequency is 49 hertz. What does it mean? It means that while we are fighting with this deficit, trying to restore the balance, we have another time counter for generators. And if running generators will be disconnected by protection, it means that we will have more problems because the generated power will decrease. As a result, imbalance will increase. Very, very complicated situation. That's why if we come back, I think it was not, it was here. Yes, if we come back to this picture and see this curve for under frequency automation operation, what we see, okay, under frequency automation could disconnect enough load to restore the balance. But where we are here, we have the low frequency. Okay, system is in balance, but with a low frequency. And what does it mean? That the next step is generator protection operation, generator disconnection, and due deficit. You see, the new deficit. But we just disconnected the load. That means that we need to disconnect new load if we have enough stages of under frequency automation. And as a result, new balance frequency will be lower and more generator will be disconnected. That's why under frequency automation, as it is here, not always a positive solution. Sometimes this is not enough to save the power system. That's why in this feature we see the second part, and it on AAF, this is in Latvian, but typically this is under frequency automation. Just divided into two parts, part number 1 and part number 2. And for the part number 2, under frequency automation 2, we call this. The task is to restore the frequency To avoid this problem that with a low frequency level, generator will be disconnected. So here from the point J, because for the frequency automation stage 2, no stage, this is stage automation 2, it starts with the time delay. This is set, it has one more set point, not the low frequency, but as a time delay as well. And this second automation will disconnect more load to make that system is with over generation. So we disconnect more load to make over generation in system, and over generation makes the frequency rise. And that's why we disconnect to restore the frequency, to avoid the situation when we lose generation. And this construction of this automation was developed in Soviet times, so was widely used in Soviet and post-Soviet countries. But unfortunately, for example, for Latvia, due to the very reliable power system and due to the reason that in Western countries this second part is not used, so there is no such automation that restore frequency. They have only this part. Of course, this is based on this protection strategy, philosophy, and so on. But the main idea that in Central European United Power, this system use this, and we have a reliable system, so we don't need this. Unfortunately, from my point of view, this is a very bad decision, because we have several examples in Europe with blackouts due to not using this type of automation. There is a lot of investigation that using this type of automation could save our systems and so on and so on, but unfortunately, yes, we are where we are. So, and next time we'll start with the discovering of Italian blackout in the year 2003, when about 60 million of people was without electricity, very huge blackout, and we'll investigate what was the reason, what was the automation operation, and why this blackout happened. And after this overview, we will talk about the design, about formula, not here, but here, about formulas, about how to formulas come in. Here formulas about the design of this auto-frequency automation, and a task with this under frequency automation calculation will be in your homework. So, and for today, this is all what I would like to say. So I can stop the record. Maybe you have questions.